This is project 4, video number 1. We've got a linear charge distribution. Lies along the x-axis of a Cartesian coordinate system. I'm going to call it the x-axis, y-axis, and the x-prime axis, y-prime axis. I'll use the primes for the charge distribution and the unprime for the position of the empty point in space at which I'm calculating the potential. So there's my charge distribution. It runs from, I'll call it L, which is minus 0.25 meters, up to U, point U, well, the point x prime equals U, which is 0.25 meters. Take a infinitesimal little bit of it, having width I think I'll do one over here to the right. It's got a width dx prime, and inside there's an amount of charge dq, which is just lambda times dx prime, or ax prime plus b times dx prime. I'll call the point at which I'm calculating the electric field, well, I won't give it a name, but I'll say it's got coordinates x comma y. And our d phi, the contribution to the electric field at that point, due to the infinitesimal bit of charge. So in other words, that point charge is just, use the point charge formula, Coulomb's law, for the electric potential. KQ over R, which is, except in our case it's a dq, so go ahead and fix that. dq we said was that, and that was dx prime. R, well, this is a distance y up, and it's just x over. So, well, x prime and actual y. So x prime gives the position of the bit of charge here, and y gives the position of the point in space. So R is the square root of x prime squared plus y squared. Note, had I picked the piece over here, x prime itself would be negative, but it wouldn't matter in my expression for R, and I would get the negative value in here, which is needed. So, R is still going to be this expression, whether x prime is positive or negative. So that looks good, actually. So it's x prime squared plus y squared. And so then I can go ahead and integrate, put those on there in a different color so it's clear that I found d phi first. And I want x prime to go from L up to U. So from minus 0.25 meters up to 0.25 meters. Alright. I'm going to break this up into two different integrals. So I got phi equal to Ka times the integral from L to U of x prime over square root of x prime squared plus y squared. Dx prime. So it's Ka x prime. I'm doing all except for that second term. Ka x prime dx prime all over. Okay, that looks good. And then plus Kb times the integral of 1 over square root of x prime squared plus y squared dx prime. Okay, so these actually look like ones that you worked with on a quiz recently. Let's take a look at the formula sheet. And each one of these looks very much like a formula on the formula sheet. Keeping in mind that y is our constant and x prime the variable of integration. So from the formula sheet, this can be written as Ka, and then I'm looking at the integral of x over the square root of x squared plus a squared, and they say it's the square root of x squared plus a squared, which will be, in our case, the square root of x prime squared plus y squared. Square root of x prime squared plus y squared. Evaluated from the lower limit up to the upper limit, and then plus Kb. This is natural log of x prime plus square root of x prime squared plus y squared. Evaluated from L to U. Alright, I think this is looking pretty good. So phi is equal to Ka, and I'm gonna change this to, no, I'm okay with that. Ka times square root of u squared minus y squared minus square root of L squared minus y squared, and then plus Kb. When you're dealing with a log, it's the difference turns into a ratio, so u plus, I guess I should do pure substitution. Kb, I tell you guys to always do pure substitution, so I better do it too. So natural log of u plus square root of u squared plus y squared, and then plus a negative Kb times the natural log of L plus square root of L squared plus y squared. And then I'm going to do something that I consider a simplification. Every term's got a k in it, so I'll factor that out. So phi equals k, and then a times and then plus b. Oh, something went wrong there. Missing the square root. Plus b times the natural log of u plus the square root of, so the difference between two logs is the log of the ratio. And that's all divided by L plus the square root of L squared plus y squared. This is positive. I want to see if this thing is going to blow up anywhere. This looks like an expression for phi. Let's look, if I was integrating over negative pieces, when I'm doing the integral, I have some negative pieces in there. We talked about r, so it's okay. If y is negative, so we got to cover pieces down here. That's being squared in there, so that makes no difference. And in terms of the integral, that's all we got, so that's okay. If y is equal to 0, we've got an integral that goes through 0. So in other words, if y is equal to 0, then as x prime is changed and it gets to a point where x prime is equal to 0, so we've got, looks like, we got an infinitesimal up there and a 0 on the bottom, so it looks like the integram blows up at that point. So let's see if that's reflected in our final answer. I think if we get issues, I don't think any of these pieces are going to hurt anything. The only place we have, something that could be, well, it could be trying to take the log of a negative number, so that would be an issue. But down here, L is a negative number. Yeah, when y is equal to 0, when y is equal to 0, this denominator becomes 0, because then I'll have the lower limit, which is minus 0.25, plus the square root of the square of the lower limit. So yeah, it looks like we've got issues around y is equal to 0. So the only way we can get rid of those issues is if b is equal to 0. Alright. Do you see that? So if b is not equal to 0, then if b is equal to 0, if we go all the way up here, we would never even have this integral. So our, that entire expression would have never come about. The piece with the natural log. Note, if I leave it like this, I've still got a problem. I'm trying to find the natural log of 0. as opposed to here I see it in the denominator, and so I'm going to be taking the natural log of infinity, or plus or minus infinity, depending on whether it's a plus or minus 0. But even here, if I say, well, let's just leave it like that, then we won't have that divide by 0 problem. Then I'm trying to take the log of 0. And you're asking yourself, what do I raise e to get 0? And it's got to be minus infinity. So it's not going to work with b not being 0. So I think what I'll tell, I'll say to the user, you just use this function with values of b with the value of b being 0. So I think we can code it up and try it, but I'd say it shouldn't work, or we'll get the function going to infinity at x is equal to 0. Alright, so let's do that. I think that was built into the project description. Let me, if you find that the code is unstable for certain values of a or b, so advise prospective user. So it's unstable for all values of b other than 0. That's what I'm going to advise them. I'll leave it in as an argument. It might be a function that one can modify. Like you could still graph from, like somebody might choose to graph from minus 25 centimeters up to minus 1, and then from 1 to 25 centimeters, so you can get the behavior of it, except for right around the origin. But we weren't asked to do that, so I'm gonna leave it like that. So I'll leave off that part of the code. So I'll just, as a bullet point, tell user to always choose b is equal to 0. So if we should be able to see what our graph of lambda then versus x is going to be. It's always going to go through the origin. Lambda versus x should be a straight line that passes through the origin, from minus 25 centimeters up to 25 centimeters. That's what our answer should look like. And then as far as the actual outline of the code, okay, I guess maybe I think I'll use the whole expression. The user can put in any value b they want, and then it won't matter if I just leave all these pieces off. Is that a good idea? No. I think I actually I'll write a message to the user. If b not equal 0, tell user treating b as if 0, b equals 0 leads to an infinity. singularity is what it's called. I'll just say singularity. Singularity at y equals 0. Alright. We know how to do that. Give the user a message. So we're going to be using an if then else statement, I think, there. Alright. Then I think I'll set x prime linspace minus 25 to 25. So that's now let's see, they put A is in microcoulombs. So I'm gonna go A coulombs equals A divided by 1e6. To get that's the A that I actually have to use in my formula, and then set phi equals, so I'm evaluating an equation up here, but I think I want to copy it over since I'm changing it to A coulombs. K times looks like I messed up on writing that down, by the way, so let's fix that up first. A times that. Let's make sure that's correct. I think that looks good. So it's going to be K-A times that difference of two differences of square roots of differences of the squares. Phi is equal to K-A times, oh, that's exactly the whole reason I wanted to copy this down rather than say just to, evaluate that formula, is because I wanted to get A coulombs. So I'll put a dot in there for multiplication, just so you know this is all one variable, and then times, it was the square root of L squared minus x prime squared plus the negative of the square root of u squared minus x prime squared. Let's see if I've copied that down correctly. U squared, oh, minus y squared. X prime is what we were integrating over. That went away. So, got lots of stuff to fix up here. Oops, that was too big an eraser. I don't need x prime, I need y. suppose we graph of phi versus y. Okay. So I got to tell the user that if you don't choose B0, it will be chosen as 0 for you. But that's a comment. I need to initialize some more variables. I'll say k equals 8.99 E9. Oops. Again, that's computerese. We wouldn't normally write that way, but I'm going to put the units anyway. Newton meters squared per coulomb squared, although we're not going to put it in the code. Then what else we got? L U I got K A coulombs, K A coulombs, L and U and Y taken care of, and then plot. Making a graph of phi versus. Oh, wait a second. I forgot about the other graph. So, yeah, I probably don't like the order of these, but I don't have to. I can put 6 and then 5. Lambda equals I'm going to have x prime after all. So I'll create them both. I know they're both the same thing. You can think of that as kind of a coincidence. The charge extends from minus 25 centimeters to 25 centimeters, and we're also asked a graph from minus 25 centimeters to 25 centimeters, but one's along the x prime axis and the other's along the y axis. So I'll create both of these arrays. And then lambda equals just A coulombs times x prime. So I'm totally leaving off the B. In other words, I'm treating it as 0, but I got a message telling the user of the code that I'm treating it as 0. That way, if they accidentally type in something other than 0 for B, they don't get an error message. Okay, so I want to tell the reader of my pencil and paper part that those two have to be interchanged. Golly, I hope you guys put those in the right order. Alright, then 7 divide I call it the plot window. You can call it the page if you want to. Window into upper region. And then 8 plot x prime comma lambda in upper region. And finally, plot y comma phi in lower region. Okay, I'll take a quick look at the handout, make sure I did what I was supposed to do. Okay, I got two things I want to do before I call this video a wrap. One, I've taken a look to see if I got a negative y value, I think it's going to work out for me, and I think so. So we said as far as phi, the y gets squared, so that doesn't matter. As far as doing my actual integral, and it's right here, but with b is equal to 0, the way I'm going to actually do it, if y only appears one place and it's squared, so the fact that it's negative makes no difference whatsoever. I think that's, yeah, what that's telling me is my graph should be symmetrical with respect to 0, given that b is going to be equal to 0. So it doesn't matter whether you're up here or down here, every contribution to the total phi is the exact same thing. And that would actually be the case if b was there as well, if there was a non-zero value of b, which we could do as long as we didn't choose y is equal to 0. Yeah, you can see this thing blowing up right there. When y is equal to 0, at some point x is going to be 0. Or x prime is, when we're doing our integration, we go right through 0. So the integrand has a singularity in it. It blows up. It's got a 0 in a denominator. Alright, then the other thing is we got to plug in values. So case let's say suppose they put in a is equal to 2, so just make up a case, test case. A equals 2. B is equal to 0, they can actually put in whatever they want, but and this is it means 2 microcoulombs, so our A coulombs is going to be 2 times 10 to the minus 6 coulombs. Alright, and what am I evaluating? This expression right here. So I'm going to call it phi is equal to Ka times, I think it was L squared minus no, I think that was a capital U. Let's see if I got that memorized correctly. Yeah, that looks good. Alright, so I think we got values for everything if we do that. This is going to be at y is equal to 10 centimeters. And at y is equal to minus 0.1 meters by inspection. So we get the same value for a given absolute value of y, whether y is positive or negative, because it's getting squared in both places. I'm only going to evaluate it here, but count it as it having been evaluated there as well. Okay, so phi equals 8.99 times 10 to the 9th Newton meter squared per coulomb squared times 2. I think I've got the units wrong. Let's see if takes 2 A in microcoulombs per meter. So microcoulombs per meter. So I'm assuming the user puts in a 2 and B is equal to 0. So 2 microcoulombs per meter is the same thing as 2 times 10 to the minus 6 coulombs per meter, and then times 0.25 is going to be 0. This is interesting. No matter what y I stick in there, because these two are the same, and then it is whatever y I stick in, I got to put the same value in both places. This is going to be 0. So this is going to be a boring looking function. We always get 0. So 0.25 upper limit, that's meters, yeah, squared minus 0.1 meter squared square root. So minus square root of is equal to 0. I think I'm going to handle that B differently. No, this is good. Well, our last project, this is going to turn out to be just an easy thing to graph. So it always turns out to be 0. I think I'll code it up and make sure that it comes out that way. But if y is equal to 0, at y is equal to 0, we have phi equals 8.99 times 10 to the 9th Newton meters squared per coulomb squared times 2 times 10 to the minus 6 coulombs per meter times the square root of 0.25 meters squared minus 0 squared minus 0.25 meters squared minus 0.1 meter squared, and that's equal to 0. Alright, so our whole graph is just going to be a horizontal line going right through 0. That's kind of, I find that a little bit funny. So what we could do to make this a more interesting project is say, exclude the region around the origin and graph the rest of it for cases where b is not equal to 0, but and we'll see that it's quite a bit different. So what we've got, once we decided b had to be 0, and that's in accord with the directions, caution the user if something's going to make it blow up, then it doesn't work for b is equal to 0. We can't do the whole graph that was specified. So once you got that, then if b is equal to 0, then a is an odd function. That is, lambda is an odd function. That is, lambda of minus x is equal to minus lambda of x. And an integral of an odd function over a symmetric integral is always going to give you 0. By the way, the 1 over the square root is an even function. So let's see if I can show that to you. So we've got an odd function once we set b is equal to 0, and this times an even function, the 1 over the square root thing. So the whole function is an odd function, and the integral of an odd function over a symmetric interval is always going to give you 0. So we get, in the end, our graph is going to look particularly simple. But let's go ahead and stick this in there, and then if a user wants to modify the code, in other words, to add this part, they can. I'm actually, I think, yeah, let's go ahead and put the whole code in there and just tell them to use b is equal to 0. So let's say use only, if they're using the code as is, they can only use it for b is equal to 0. Then we'll see what our singularity, how the graph. Oh no, that's right. If we do stick in a b there, then it's going to have trouble actually analyzing that. So the code will try to do this division, even though in the end it's going to be multiplied by 0, so it doesn't matter. It'll find a 0 in the denominator. So I say we'll go as I mentioned what our original plan was, and then we'll program it up, but let the user find out that you just always get 0, no matter what it is. So I got the code outline, I got my checks. So I guess this was phi at 0.1 meters, phi at minus 0.1 meters equals phi at 0.1 meters. So phi at minus 0.1 meters equals 0. So additional work after that one. So I've evaluated at 0.1 meters, at minus 0.1 meters, and at 0. I get 0 in all cases. Let's call it a wrap on project 4, video number 1.